Welcome to everybody for this session on autograph. Autograph's been around for a long time, since about the 1990s, so it's possible some of you have used it a lot, some of you are perhaps new to it, and we'll hopefully cover both this afternoon. We're going to have a welcome and an overview of autograph to start with, followed by lesson ideas in shape, algebra and graphing, vectors and calculus, data and statistics, and then some Q&A at the end. So it's quite a broad range of activities, and I hope you'll find this useful. So the first session is just a summary of a few things that I think make autograph rather special. We've got to remember how autograph happened. It happened because I and colleagues were teaching, and we thought, wouldn't it be nice to be able to see mathematics as well as think about it? So that's the background. It's evolved substantially now, and it's now on version 5. And we start off with a little problem on area of a triangle. Here we have a simple triangle, and it would be quite nice to discuss what the area is. But before that, I've also got a little line segment here to have some fun with. And over here, those of you who are new to autograph may not know that the point mode extends now to various other modes, including line segments. So let's put another line segment down here. Can we put one that is parallel to that one? And is it? Well, we can test for that now. Select that and select that. And one of the right-click options, the right-click has been expanded considerably for autograph. And one of the options for line is a parallel test. Aha, yes, it is. And also an equality test. So you can move these points around. Can you move them around so that you get another perpendicular? Well, this is 2 to the right and 4 down. What about 2 up and 4 up? Can't quite make it, but if we pull this one down, that'll do it. And there we have both equality and perpendicularity. Over here we have a triangle. If I select that and this line segment down here, not the area, sorry, take the area off for now. Just going to select the point and this line segment, you can have the closest point. That's obviously is instrumental in working out the area of this triangle. To be able to show what the area is, I think it's very good to be able to select those and create an area, shaded area. And that area can be displayed using the on-screen calculator. Calculator is really, really useful, because every object now in autograph has a set of attributes. In this case, the attributes are the perimeter and the area of this shape. If we go area, you can put some text before area equals, and then it shows here. I can't spell, but it doesn't matter. So that feature is really useful. Obviously, you can put the midpoints on and show that they're parallel as well. So the next topic, I thought we'd have a look at some regular polygons. Autograph now, very simply, if you just put a couple of points on in a clockwise manner, you can create a polygon. So right-click, create regular polygon from 2 points. Yes, lovely. How many do we want? Let's put in 4. So we'll just recreate what we've got up here. And the really nice thing about these polygons is that there are points on each vertex. So you can take these 2 and create another one. So right click, create polygon with 6 sides this time. 2, 4, 5, 6. So what we might be interested in is fitting a polygon between the 2. So I've now got as far as this one has, so I may as well just sweep that one to one side. I've put 3 on here. If I select it, the lightning wakes up. You see, with nothing selected, it's not there. But it means I can animate the main parameter that makes this thing work, which is the number of sides. So I can go 4, 5, 6. So how many sides do you think is going to fit this? Very nice, 12. and you can work out the angle between these two, for example. Again, with a clockwise motion, select 3 points and clockwise the angle, right-click, create angle, and it will be 90 degrees, yes. The next topic I thought was quite nice, which is taking a picture off the internet. And the internet, of course, is full of wonderful pictures. And I got quite a collection of these on the autograph resources, which is in help autograph resources. You can pursue that and get lots of ideas for shape for pictures and also spreadsheets and data as well. Okay, so mathematically speaking, we've got something which looks parabolic, and if you're teaching A-level mechanics, of course, you know that it's parabolic, and the parabola will follow the centroid of this poor unfortunate creature who's put his life in his hands to try this incredible feat. I mean, it could be a fix, actually. I just don't know whether it's actually happened, because goodness me, you've only got to be this tiniest bit out with the velocity and that angle, and he misses the net altogether. So what are we talking about here? We're talking about enter an equation, and it's going to have the form of y equals ax into, now is it x minus b or is it b minus x? It's a good question to ask. We want x squared to be positive. No, we want x squared to be negative. We'll try it this way up and see how it goes. Ready, steady, okay. Aha. Now that's because the value of a is the wrong one. So let's just take it now. What it should have been, of course, is b minus x. So the x squared term is negative. Now, a and b are both 1 to start with, which is why it's going through 1 here. Now, this is where the constant controller kicks in, and autograph has this rather than slider bars for lots of very good reasons, I feel. If we look at b now and just increase the step to 1, we can keep going, and of course, each time we do, that is the value of b. We can stop around about there, but you can adjust the step and make fine adjustments. That's probably about right. A, what about A? Well, A is 1 at the moment. If we go down, it will be that, then reduce the step and up we go. See how useful it is to be able to dynamically change the step. That's really good. Other images you can get off the web, which are quite useful in autograph. This image from Australia, and the west coast of Australia, it looks a harmless hexagon, but actually it's an enormous one. It's 1.4 kilometers along each edge. Turned out to be an aerial system for communicating with submarines in the Indian Ocean. But there it is, and you've also got another one on the inside, and it's a good exercise to have a look at this one and see if you can manipulate it to sit on top of the big one. It's an enlargement and it's a rotation. This is a very common request to link circles and trig. What I've drawn here is a circle, center -1 and radius 1. And I've set the scales. If you just double click on an axis, you can see you can set the scales to multiples of pi, which is very nice. As you move this around, so the point goes around the circle. Well, so what? This point has parameters. It has an x and a y parameter, and it also has a parameter of the angle around the circle. So let's see if we can make use of that. So there's another very good feature of autograph now, which is managing constants. And if you manage the constants, to make it an attribute, I'm going to take the constant a to be the angle. You just click on this, and there it is, t. Add that in. And I'm also going to do b, which is the height of it, which, as you know, is the sine value. So b, an attribute, and click on b and add it in and close. So what's that going to produce? It's going to produce a point that's over here. If we now create a point, enter coordinates, and we do it a, tab, b, a will be the angle along this axis, and b will be the height. So it should be sort of over there somewhere. And there it is. And that's very good. And those two can be linked because this is a point that depends on this one, and this is constrained to move in a certain way. So you can make that into a locus, create a locus. And 16 is probably enough. And what is lovely is you can move this around and see how it fits into the locus. Lots more you can do on that, but we must push on. Inverse functions, it's in the GCSE, quite a complicated idea. So that made me think that let's use this idea of redefining a point according to attributes. So there's a button up here called XY attribute point that we're going to use now. I'm going to select this point that I've just randomly put over here, and it has two attributes, its X coordinate and its Y. So if I create a new point that's the other way around, I'm going to make that the Y and this the X. Where's it going to go? Well, the X at the moment is -3, so the Y is going to be -3, and the X is going to be 2, so it's going to be over here. Yes, and that's a characteristic autograph technique, is to try to anticipate what's happening on the screen before it actually does. Then if I move this along, if I move it to the right, what's going to happen to this one? It's going to move up. And then if you attach it to this line, you can see that what we're creating is an inverse function. Lots more to that topic, of course, but that's quite a nice introduction. Then I think we'll move on to three ways of looking at the quadratic equation. Now, there's the formula, which everybody's very familiar with, and here's the quadratic equation, and it has two roots. Well, does it always have two roots? Well, let's have a look. We open the constant controller now. C at the moment is 0. So if we increase C, you see that I've done some of the algebra here. I've deliberately chosen a quadratic which has 2 as the coefficient of x, because that means all the 2's and 4's cancel out. So the roots are actually 1 plus or minus the square root of 1 minus c, which is okay as long as c is less than 1. So what happens if c goes bigger than 1? So we just go up to here. Well, at c equals 1, you've got no root, you've just got one single root, and then we have to say, well, you have to imagine it's bad luck. I'm always very disappointed when I hear that really favourite topics have disappeared up into further maths, and this is a good example. Further maths has all the fun now. It has volumes of revolution and complex numbers. So is there another way of looking at this? Well, yes, there is. Because autograph now has a complex numbers page, an Argand diagram page. So exactly the same algebra here, but now we've got a different constant controller. And we move this up and down, and you can see you've got 2 complex roots at the moment, then you've got 2 real roots. But then I've long thought that actually the Argand diagram really should be in 3 dimensions, because this is x, and there's y, but this is sort of a z in a way, isn't it? So let's have a look at this and take a look at this in 3 dimensions. And here's our same quadratic. We've got x along here and y up here. That's the Argand diagram. But what we'd like to know, sorry, this is the Argand diagram, x and im. So the new axis is this one up here, y. So now if we increase c, we need our own constant controller. You can see that as soon as you go up there, you get 2 complex roots. Just to finish off, to show that there are lots of shapes and things you can do in 3 dimensions, which is just wonderful. Good. I'm going to pass you back to Rob now, who's going to have a look at some shape ideas.
Thank you, Doug. And yeah, like I said, it's been great to run the autograph training courses with you, Doug. And I'm just going to quickly just show people where they can find those materials. If you go to the Complete Maths website, you'll see we have the autograph tab where you can actually download autograph for free. And recently, Douglas and I have been running the Beginners Course Masterclass, where we've created some how-to guides and some autograph files to support those. So hopefully these are ideas that you could take away back to the classroom and you can use with your pupils. Now, one of the main reasons for running this session was so that we could talk to you about using autograph for teaching and learning mathematics. And I want to think that autograph has an intuitive interface for both teachers and pupils. At the moment, I'm in advanced mode, but I'm just going to switch back to standard mode for a second by just changing the preferences, and that will just simplify a couple of my toolbars. On this left-hand toolbar, you see we have point mode, and I can just create some points. It's as simple as selecting the shapes and grouping them to a shape. I've got another point here, and I can select a shape, and I can create a rotation, and I can show the construction line. I can just zoom out, and you can see there that I can select my object, or I can select my center of rotation, and I can show pupils very easily what happens when a shape gets rotated. I can, of course, instead of rotating by a particular angle, I can use what Douglas mentioned earlier, which is the constant controller, which allows me to animate, and I can manually animate, or I can actually create a repeat animation. And I'll just slow down the speed of that for you and click play. And I can show that that's going in an anti-clockwise direction. I can stop that. And if I wanted to, I can just change the direction as well. So as you can see there, that rotation and animation, really simple to create. We've created some examples here that we've just run through. We can measure the angle of rotation and display that. And again, we can move the object. You can see what happens. The angle is staying the same, and we can move our point. We've got enlargement, where we can actually do calculations. So if we just click the calculate button here, and the object or the image, I can actually use the attributes of those. And as Douglas said, it's as simple as just putting the area equals. One of the other fantastic features of autograph is the online keyboard. And you'll see that when that keyboard pops out, I can actually use that. I'll bring it onto screen for you to see. I can actually use things like the superscript and subscript. So I can actually put my units in there. We're not going to focus too much on how we create these activities today, because you can, of course, come on the beginner and intermediate course that we have with all the how-to guides and resources available. Here we've created a reflection, and we can reflect in a single line, or we can reflect in a equation line. So I'll just demonstrate how you might go about doing that. So I'm going to use a square. So again, just points, group to a square, and I can just select the object and reflect in the y-axis. Now you can predict where that's going to appear with your pupils, but again, you can see I can move that horizontally and vertically. At the moment, I have my snap settings to go in whole units, so you can see whole units in the toolbar, but if I change it to tenths, I can actually move it anywhere, and we can have that discussion. To enter an equation is simple. You just enter the equation, y equals x. And if I want to select my image and my line, and I can just right click and reflect. So now I've got the two linked together, and you can see what happens there. So I'm reflecting in the y-axis and reflecting back in the line y equals x. So we might want to know what the translation is from the original shape to the image. Well, I can just put 2 points and select them and create a vector. And there's a 2-point vector. And if I just display the text box, that will give me the details for that vector. You can see it's 1 square across and 1. So if I put 1 point on the vertex here, and the other point with the same vertex, you can see it's a translation of 2, 3. I can obviously move my text box. And another great feature of autograph is that I can edit the fonts and the labels. So I might want to change the size of the font and the color. all these customizable features within Autograph that allow you to then screenshot and save out. Now you can see on the page options, I can just copy the page as an image or copy the graph, and I can just paste that into Word. So that's really useful. We've looked at translation by a vector. We could do multiple transformations. We've got reflections, rotations, and enlargements here. One of Doug's images taken from the internet, and we can measure the angle and bearings of airport runways, and we can explain to pupils why we might want to do that. Doug and I created this example here, which shows that we have a trapezium, and if we rotate around that vertex there, the midpoint, we can create a parallelogram, and we can calculate the area of that by just selecting and clicking the area. And we can see there that has an area of 21.8. Doug's already demonstrated the polygons using the constant controller, but one of the things that I think is useful to go away knowing how to do is how to create the circle theorems. And so we'll just have a go at creating the angle at the center is double the angle at the circumference. So create a circle of radius 3. I'm going to need 2 radii, 1, 2, and I'm going to need an angle at the circumference. And I'm just going to collect 1, 2, 3 points to create the angle. And you can see there that's currently 47 degrees. And so the angle at the center we're expecting to be 94. Indeed it is. And wherever I move my point on the circumference, you can see that angle at the center remains double. I could, of course, move this angle, which will change my angle at the circumference, but there's 74 and 148. And if I come round into this section, well, we can see that we're actually calculating the angle over here. So we should be able to select those points and create the reflex angle for there, or the other way around. 1, 2, and 3. Create the angle. There we have the 212 and the 106. So now, when I move this round, you can see we've got the angle at the center, albeit I need to move my reflex angle round. We've also got the alternate segment theorem. Again, a nice easy proof. We've got a chord bisected as a perpendicular. We can literally select 2 points, and we can right click and create the line that is the perpendicular bisector. Or you can do what Doug's done there, which is create the closest point. So the point and the line, and we can create the closest point, which will create the perpendicular bisector. Here's an example showing that the cyclic quadrilateral, we've got the angles. We can see there that they all add up. So we'll use our calculator, and we'll just steal the attributes from each of these angles. You can see 1, 2, 3, and 4. 360, and that's all our angles around in a cyclic quadrilateral. We might want to prove it by using the line test that Doug talked about earlier with the equality here. We can add labels, we can change the colors and the transparency, and we can also have this line segment. So lots of useful features there. Again, I'll talk about this rotation animation. Just select the image, click the animation, and we can just rotate that round, and there we have it. So hopefully you'll see how intuitive and simple that was, and by no means have I been using Autograph for that long, but Douglas has been teaching me on the beginners and intermediate course how to do a lot of these features, and I'd like to hand back to Doug to run us through the next little section. Hopefully you'll be able to go away with those support materials, and you can just find out how intuitive Autograph is to use in the classroom. So Doug, may I hand back to you the screen share?
Okay, here we go. And one or two topics here to do with algebra and graphing to play with, finishing off with fitting a graph to McDonald's M. We'll start off with completing the square. Let's close all these down because we finished with them. One really nice feature about Autograph, of course, is that all the previous work is here. So if you can't remember what we did in the last half an hour, just wander back through all the tabs, and here they all are. Now, completing the square is a slightly tricky topic. So what I've done here, I've drawn a parabola, x squared minus 3x minus 1, which is this fellow here. And we're going to rephrase it as a square, so x minus a all squared plus b. But I've set a to be 0 and b to be 0. So what we do now is start off with the constant controller, because what we need to do is play with this new factorized version and see if we can make it into the red one. So first of all, let's change b, not unlike how we did with fitting the parabola to the human cannonball. Okay, if we increase b, it's going to move to the, which is it? Now, plus b, it's just going to move the thing up and down, isn't it? So I think probably we'll do a first, second thoughts. Now, it's x minus a. I'm a massive fan of x minus a, not x plus a. I see x plus a far too often. X minus a means it's a symbol, it's a movement to the right. It means it's where the vertex ends up at. So when a is 1, vertex moves from here to here. So it moves to the right. Now, also, one of the other options in the point mode is to look at intersections and other interesting points. You've got an intersection here, you've got an intersection here, but you also have the minimum down there. And with that one marked, I'm going to right-click line, put a vertical line, just to show where the minimum value is, because we want to make sure that this one is symmetrically placed around the green line. So on we go. And it looks like we've done it. It's okay. There's no need for any further work on that. But b, let's move it down. The whole thing shifts down. The good thing about this form, I mean, we could think of this as y minus b equals x minus a squared. Then it's quite clear that x and y both being transformed by a and b. So let's move this one down. And I think we're going to just miss it. So again, really useful to be able to change the step dynamically and move it back to where we think it's about right. If we're not sure about that, let's just zoom in. Yeah, that's spot on, isn't it? Now, don't worry if when you're zooming, you lose the plot. That's my only joke today, by the way. Let me introduce you to the red tick. Red tick will just bring you back to sanity. So what have we done? We've taken a y equals x squared and we transformed it down to here. So if we start off at the origin, so let's do enter coordinates at the origin, and let's put a vector there of a tab b. That should bring a vector right down to this point here. Let's see if it is. Wow, fantastic. Okay, next topic, inequalities. Another one of my favorites, because I suddenly thought, could technology help here? And let's just see what I've done. I put a point here, but I'll take that off and put it on again so you can see what I've done. First of all, 2x minus 3y is less than 6. This is a classic for the slow plot, and obviously I haven't told you about the slow plot yet. That's what it should have done. We should have plotted across here, and you can stop. Too late. That's replot. Okay, and pause. Where's it going to cut the x-axis? We're going to cut the y. Well, when x is 0, y is negative 2. When y is 0, x is 3. So lots of chat about, and just see that that's the way it's inevitably going to go. So we take the brakes off. What about the shading? Well, it's a dotted line because it's less than 6. If it was double-click less than or equal to 6, and you just put an equal sign after that and it changes, it becomes a solid line, which is the right convention. Is it shading the correct side? I always like to shade the reject side. In other words, it's not obeying the inequality on this side, but it is on this side. So that if you've got 2 or 3 of these, you leave them all clear here. But some people prefer the other way around, and it's View, Preferences, and you just switch it over. I thought that it would be really wonderful to have a point here, and let's have a nice visible point. So edit, draw options, and let's make it a triangle and nice and big. Okay, so once again, our friend the calculator comes out, because I'd like to work out what 2x minus 3y is at this point. So I just go 2, it's calculator notation, so 2 times the x coordinate of this point, there it is, minus 3 times the y coordinate of this point, and then here, the text before is 2x minus 3y equals, and off we go. Well, it equals minus 2 at the moment. So does that agree with this? It's certainly less than 6. So it does. So it's on the agree side as opposed to the disagree side down here. But we can move it around. And you can see that it's being reevaluated all the time. As soon as you cross the boundary, it's more than 6. Well, I just thought that was great when I first thought of that. Okay, what's next? This is something I've done with even quite senior students. And I've given them y equals x squared. And I say, right, just come along to the board and see if you can draw y equals x cubed. And you get everything. A lot of people think cubes are going to be like this. So yes, okay. Then you start looking at it in some analysis. And this is where the pen comes in really helpfully. I need to get my tablet out because it's easier on the tablet. If you've got a tablet, by the way, it is nice. You can walk around the room. So it definitely, when minus 1 cubed is definitely minus 1. 0 cubed is definitely 0. 1 cubed is definitely 1. Aha, so it's a straight line. No. So what's it going to do? Think when x is a half. It's going to be a half of what it was when it was squared. So a half cubed is there. And then a quarter cubed and so on. And up here, and then beyond 1, it definitely gets bigger. Over here, you've got the similar pattern. And of course, they're terribly impressed if you get this right. But let's just see. Y equals xxx. What we've got to do to get x cubed. Slow plot. Time to go through it in detail. Not bad, but with a bit more practice, I could have got better at that. Another topic I thought we might cover is velocity time. It's in the GCSE syllabus, taken by 16-year-olds in this country, but why is it that the area under velocity time is distance? You can prove it easily with calculus, but without it's tricky. With straight line segments, it's not so bad, and obviously we can use the calculator to work out the distance traveled. Notice that the axes have been labeled velocity and time. That's all done here, double click, in the edit axes. Labels, I've changed the x variable to t and I've changed the y variable to v. So we could actually put equations in v as a function of time and it would plot them correctly. And here are the velocity and time labels with units, of course. So there's another one, it's slightly more sophisticated here. We've got a very similar situation. You've got the velocity increasing and then steady velocity and then decreasing. What I've done here is that I've put a point here and a random point here, and I've worked out the area underneath this graph. This is a piecewise graph, of course. It's 2t, 4, 8 minus t. And using the xy that I mentioned before, I'm making a new point that takes its x from the x coordinate of b and its y from the value of the area. And so you get the idea of an area function. It's parabolic here, it's linear here, and it's parabolic here. No time to go through this in detail, but if you come on one of the courses, obviously you can find out more. It's all about visualization. Now, what about the equation of a circle? Here I'm going to select this point here and right-click Circle Radius. So I'm going to put in a radius of 3. That'll be a circle roundabout here. What will the equation be? Think about it. If you're teaching this as a topic, then it's nice to have the information at your fingertips. So text box, there it goes. So it's a mix of x plus 2 and y minus 3. Now, which is plus and which is minus, and why they're this way around? What about the coordinates? That's minus 2, that's plus 1. Yeah, okay. So if I move this point 1 to the left, what's going to happen to the equation? Aha, yeah, x plus 3. But, you know, it's just nice to think about it, and it's just so counterintuitive, really, because you don't expect all the minuses to be on the right-hand side, but it's just like I was saying in the previous exercise. And of course, up and down changes the y. And obviously, r changes the radius. What I thought I might do, actually, just to finish this off, is to have a look at some trig data. And the most general trig equation and the transformations thereof take a very specific form. Y equals a sine brackets bx brackets. I don't mean b, I mean, yes, b brackets x minus c brackets plus d. A represents amplitude, B represents frequency, C represents a translation to the right, and D up and down. Okay, all the values are 1 to start with, but I think I'm going to make C 0, and I'm going to make D 0. So it should be just a straightforward sine wave. Yep. Okay, so what I want to do now is play around with the constants and try to reinforce. This is some data from some tides, tide going up and down with time, and it's very much like a sine wave. So let's see, if we change A, it's just the amplitude. Yes, that's probably about right. If we change B, it's the frequency, so that's probably about right. And C, let's move it to the left or to the right. Let's increase the step. A little bit more, maybe reduce the step. And D, move it up and down. Not too bad. But actually, you can ask the computer to do all the final sums for you. But as an exercise in understanding what the various parameters mean, I think it's very important. You can create now best fits data, and it will sort it all out. And there we are. And text box. There's all the things. So a nice little exercise. McDonald's just got time for. Just quickly put this one in. A couple of parabolas will do nicely. What about this one? So it's going to be y equals a into b minus x. Again, it's a sad parabola, so it's that way around. And we need an a at the start, just like we did on the other one. So it's going to start here, and because b is 1, it's going to up here and down there. Okay, again, try to predict as it goes along. So increase b. That's not bad. About 3.6, that'll do nicely. And then a, move it up a bit. Okay, that'll do. We want it to stop here, though. We don't really want any more than that. So double click on the graph, and the startup options are really important here. We're going to do it manually from x start at 0 and finish at b. So it'll only plot one little bit. While we're at it, let's make it a bit thicker so you can see what's going on. So now it starts here and it finishes here. However, we want to get the other side in too. And the simplest way of doing that is to change the x to the modulus of x. So I'm just going to put in a modulus sign here, which is this one here. Or if you know your way around your keyboard, there's one just between the Shift key and the Z key. There it goes. And of course, the startup options now, we want to go from minus b, otherwise we'll miss half of it. Okay, okay. And there we have McDonald's. Okay, and let's go back to here again, and some ideas of vectors and calculus, sort of favorite topics of mine. I'd spent most of my teaching career with the students saying, oh, I hate vectors. But then so when they started to look at them moving around the screen, I see, that's what's going on. So we'll have a look at a little problem I've set to do with a couple of battleships. Here they are, and we've got a battleship A, and it's going at a speed of 1 unit to the right and 1 unit down. Battleship B is going at 1.5 to the right and 2 up. Now, it's a basic principle which we've already discussed, is that the displacement, the distance traveled, is equal to the velocity times time. So if that's the case, all we need to do is take this vector, double click, and here it is, and multiply each one. It looks like I've already done it. It was 1 minus 1, and now I'm making it t minus t. And that way, you'll see that as I change t, which of course is another parameter, so I'm going to open the constant controller and increase t, and you can see what happens as t increases. That's lovely. So where is it closest? Well, the classic approach to this is to reduce one of the ships to rest. So I'm going to take this vector and this point and right-click vector, negative vector. Perfect. And that vector I'm going to add on to the ship A. Not there, go away. That and that point, and right-click vector, copy vector. Okay, so basically B is now motionless, not going anywhere because it's got equal velocity in both directions. This, though, if I add these two vectors together and put the answer here, right-click vector, add, this is the direction the ship A appears to go from by observer on ship B. So we just keep going here, and the minimum closest point would be from here to here, right-click, line, perpendicular line. So that is the time at which they are closest. Obviously, you can zoom in, take a closer look if that would be helpful. Now the calculus is wonderful, and there's so many visualizations that really can help the students to understand what's going on. Just trying to look for my mouse. There it is, just a bit off the edge. Okay, let me introduce you to my favorite cubic. Y equals x minus 3x minus 1. Why is it my favorite cubic? Because it has a maximum at x equals minus 1. It has a point of inflection at x equals 0, and a minimum at x equals plus 1. So we'll click OK and just see if that's right. The sort of discussion you want to have now is which way up is it? Well, x cubed is, when x is negative, x cubed is very large and negative, so it's coming up here. When x is 0, y is minus 1, we've already discussed that, and then it goes. So it's going to be this sort of shape. That's the sort of chat to have before it plots it. Then to sort of reinforce the idea, I've just grabbed this picture of a skier off the web, and I'm going to put a point on the graph and select the point and the skier and right-click attach to a point. Boom. Ooh. Double-click on the image, scale image with axes. No, thank you, because that's messing it around. Then just make it sure it's perfect. There you go. And you can see that get an idea of gradient from this. Something quite special happens here. It's clearly horizontal, and it's horizontal here. And here is the steepest it gets. As any skier will tell you, I'm glad to get this far without falling off, because it's then definitely going to level off. And of course, you can animate this if you want to, from minus up and down. Why not? There's another topic on discovering E. Nearly always all the lessons on this start with 2 to the x and good old 2 to the x, and of course discuss it in slow motion and so on. And when x is minus 1, it's a half, it's a quarter, and so on. Let me introduce you to the gradient function now. This will basically draw the gradient of the parent graph and draw a tangent on the graph and show what the gradient is. Well, you can see that it's sort of similar. What we're looking for is a function that is equal to its own derivative. So can we vary A? Yes, we certainly can. And here is the constant controller now. Now I'm going to increase A from 2 to 2.1. Again, get the pen out and just discuss this. This point's going nowhere. This point will go up to 2.1, so it's going up. This point's going down because it's 1 over. But this represents how steep this is. And if this is going nowhere and this is going down, that's steeper. So that's going up, and this is going up as well. So that's a sort of chit-chat to have before you press a button. You can take it now, and as it goes and goes, 2.7, job done, yes? Well, if we just drag the whole thing down here and then start zooming, this is where it really is very intuitive. You can split them apart. And if we go back to this, now if we do that one, it's almost certainly going too far. This is where the changing it dynamically is so useful. And then reduce the step again, and back we come. And do a bit more zooming. There we are, 2.71828, not bad. What about integration? It's the next one to do. And what I've done here is that I've selected 2 points on y equals x squared, and I'm going to create an area. Gosh, it's almost off the bottom, but I hope you can see that. Create area. I'll take the general one, but you can see there are lots of options now for areas: midpoint rule, trapezium, Simpsons, rectangles, and so on. Just a general area. And I'm going to do what I did just now. I'm going to select the point and the area and x, y. So I'm going to take x as the point, as the x coordinate, the y coordinate as the area. What's the area here? But be a point round about there somewhere. There it goes. So what is the area function? We're getting used to the idea of a gradient function, but an area function. Well, if I select these two, I should be able to do a locus. This is constrained to move along here. This is linked to this point, so perfect for create locus. There we are, it went all the way, but that doesn't matter. Okay, we can move this around and see that that's the area function. We're sort of used to the idea of it being 1/3 of x cubed plus a constant. Where's the constant coming from? What about this fellow here? Aha, that's what it is. There's his constant 0 at this point. So 1/3 of x cubed plus a constant. Another look at area is to say, well, exactly the same one from 1 to 4. The area appears to be measured using rectangles as 2.185. You can select that, and off we go. So what happens in the end? Well, it'd be quite good, I think, if we go to page settings and bump up the sig fig, because we know what the answer is. It's 2.3 recurring. So is it ever going to get there? Well, we could double click on this and no, let's do it. First of all, let's have 100. Is that going to help? Well, at least it's got the first 3, but there's a lot more to go. If we zoom in on this, you can see what's actually happening. And then students may say, well, this isn't a very good way of working out an area. It only works when you've got an infinite number of these. Well, okay. How about using a trapezium rule? Good idea. So let's just put the information up about the area. I'm selecting that and the text box. So the area is 2.31835 at the moment. If I was to change this to a trapezium rule, which would appear to be an extremely good solution, is it going to be more than 2.3 recurring or less? I suppose I should get you all to vote on this now, shouldn't I? But there isn't time. And let's have a look and see. Aha, just over, isn't it? Now, why is that the case? Well, if we zoom in, this is where technology really does do things that you can't possibly have done before. And you should look out for the red line, which is the equation, and the green line, which is the trapezium rule. And that's why it's a slight overestimate. Well, there are some vectors and calculus, and then we're going to finish off very quickly with some data and statistics. And inevitably, this is the one that tends to be at the end. But you can see there's lots of visual things here to do with scatter diagrams, box plots, normal distribution, time series, and so on. So let's have a look at these. Okay, so first of all, I'd just like to do something really simple, and the simpler the better in lots of ways. Scatter diagrams, that's what I'm trying to do. I've just basically got a page set up here, just a few points, because I think you can make some points. This is X and Y, so I'm just going to do 1, 2, 3, 4, 5 points and select them. Okay, and I'm going to, what can we do with it? I'm going to make it into a data set. So if it's a data set, it means it's one object rather than 5. Just one click, and if you double click on this, there they are. That could have come straight out of Excel, of course. Don't perform an but cancel that. So right click, what can we do? A point, mean, perfect, look at that. And right click, line, regression line. So the first thing you'll notice is that the regression line goes through the mean. We also are making it quite clear that any point, any reading outside this region is unreliable as far as extrapolation is concerned. Doesn't mean it's wrong, it just means it's unreliable. Now I'm going to press the Control key and move this around because you can't move it otherwise. And you can see that whatever you do to this, the regression line always includes the mean. Some very good lessons there for simple XY plots. You can do the same in single variable. Now the various page types along here, that's the complex numbers, the 3D graphing, 2D graphing, and now 1D stats page. We've only got one variable, so this is where you put in all the probability distributions and raw data and so on. I'm just going to have a look at putting in the point mode, just clicking away and looking at some data that's sitting down here, and then perhaps one out here as an outlier. So just like with the XY, I'm going to select that lot and convert it to a data set. And now I'm going to do a box plot. And here's our outlier as predicted. Outliers are 1.5 times the interquartile range. So anything beyond there is an outlier. Let's have a look at that. I've got control still down from the previous one. It means I can move these points along. It should, there it goes. And you can have a look and see what fun you can have with box plots. You can also get box plots from data. I've got some data here, and this is one of the examples produces this. Very interesting data about the life expectancy at birth. And if we just drag from here to here, just show how easy it is to produce one, I'm just going to copy that. Well, I thought I was. Let's try that copy. There you go. Multiple selections. Don't understand what it's doing. Is Excel being silly? There we are. Okay, and so now we have one of these, and right click, enter raw data, right click, paste. It's that simple. In it goes. Take all the defaults, what the heck, and see what happens. Right click, box plot. So there you have our first box plot, and it's not very difficult, obviously, to produce lots more. Let's just have a look at that. So all I've done is done it lots of times, and you can see that it certainly pays to be female if you're living in the London boroughs. There's lots of other things we can do, but I think time is against us now, and we have to stop shortly. But I'll just show that basically probability distributions are very nicely done. Normal distribution, binomial, and Poisson. If you take a normal and try, say, mean of 100 and standard deviation of 15, which is the old IQ test. There it goes. You can very usefully, I think, select it and draw the mean and 3 standard deviations, because you're never going to get much outside that. You can do calculations on the normal distribution, probability calculations, including the reverse one. So if you want to find out where the 10% region is, one-tailed or two-tailed, one tail is going to be around about here, I would say. Yep, there it goes. And obviously, if this is your H0, and you have a point in here which you think is enough to reject H0, but H0 is in fact true, that of course is a type 1 error. I will just finish off with some data from COVID. And this is data from just the other day. And you see these charts on the telly all the time. And we grab from here B to C and copy. If it's going to allow us to do that, that's good. This is grouped data because we know the frequencies already. And we're going to put it in as an XF table. So right click, paste, there it goes, and click OK. Now we probably want all these to happen. Click OK, it's discrete data, and off we go. So there are lots of diagrams you can do here. You could draw a basic histogram. That's quite messy, but or we can do a line chart. So I think I'm going to take the histogram off because it's looking a bit of a mess, but the line graph, you can then create a moving average. And it's weekly data because that's the way it's structured, because things happen at the weekends. And if we hide this, there is the diagram for deaths. And the 23rd of March is when we went into lockdown. And we're now about here. So, you know, it's promising, but gosh, we could have done without all of that. And if you want to see what it looks like compared to Italy, all put together, Italy was basically 2 weeks the other way. That's how it actually was. But you can see this moving Italy to the right and scaling UK down by 67 to 60. The astonishing resemblance.
Well, Doug, I'm going to have to steal the screen from you there because
That's
we've
okay.
literally got 2 minutes left. So I just wanted to mention the forthcoming autograph course. We're repeating the beginner's course. The session 4 is on June 24th and also on the 23rd and 29th. There are YouTube recordings on the Complete Maths website that people can have access to, the how-to guides, and also onto the autograph files and the tasks there. They are available. Here's the link. We've got the intermediate course coming up in July. So on Wednesday, the 1st, 8th, 15th, and 22nd, hopefully you can join us for some of those sessions where we might be able to go through at a bit of a pace and show you how to create some of these sessions. So, you know, Douglas and I would love to see you at those sessions. If those sessions are full, if you contact the LaSalle team, we might be able to squeeze you in now that we've had MathsConf23. We hope you've enjoyed the session. And if you've got any final questions, if you can drop them into the chat. Doug, if you can just take the screen for the final thank you for attending slide, and then we'll end the session there. But if there are any questions, just drop them in the Q&A, and hopefully we'll be able to answer those for you.
Here's the final one. Try to say thank you. And just a final thought. There's a lovely problem that was set recently on Twitter. And that was one solution. And let me tell you that there's a much neater another one. And that's done in about 10 seconds. So it's a good example, I think, of autograph playing ball beautifully. So here we have our thank yous. We've done those and that. And thank you for attending.